All right, let's take a look at these notes talking about proving lines parallel. So the last section, we were taking parallel lines and showing properties from knowing that there's parallel lines. And now we're taking properties and showing that there's parallel lines from that. So it's the opposite way around. It's what's called the converse. So let's just go on with this review here. So 1 and 5, those are corresponding angles. 1 and 8 are alternate exterior angles. 2 and 7 are inside of the parallel lines, so they would be alternate interior angles. And 4 and 7 are same side interior angles. Now, if you remember, for these 4 angle pairs, all of them are congruent under parallel lines except for same side interior, in which case those were supplementary. Okay. Those arrow lines mean that the lines are parallel, which is something we have to look out for if we want to say that these angles are congruent or supplementary. It doesn't exist, doesn't happen unless they're parallel. Okay. So a little bit of a note of logic and what the word converse means I said earlier. Just with some examples here, if-then statements called conditional statements are really the building blocks of math. So I have a few to look at here. So if today is Saturday, then it's the weekend. That would be always true because there's never a weekend without Saturday. If x plus 3 is 7, then x is 4, that's always true. All right, because if that equation is true, then x is 4 is true as well. They come hand in hand, true and true. Now, if 2 lines are coplanar, then they are parallel. So imagine we had 2 lines on a piece of paper. Yeah, it looks like that they'd be coplanar, but they don't necessarily have to be parallel, because we could have an X on a sheet of paper. So this would be a sometimes true thing. Well, what's interesting is with these if-then statements, if you reverse the if and the then, it's called the converse, and it actually has a pretty big effect on the statement. So for example here, if it is the weekend, then today is Saturday. If it's the weekend, then it's Saturday. Is that true? Well, it sometimes could be true, but not always, because it could be Sunday. The converse here is if x is 4, then x plus 3 is 7. Yeah, that's true by the addition POE, right? Always, sure. And this one, if lines are parallel, then the 2 lines are coplanar. And that is always true by definition, because we defined parallel lines earlier as being coplanar and not touching. Okay, so sometimes, for the middle one here, it didn't matter if you went forwards or backwards with the if-then. And when that's true, that's called a biconditional, meaning 2 ways. It's both if-then and then-if kind of thing. Right? So those are called biconditionals. And sometimes we use this symbol for a if-then. And if you have a biconditional, you would use a double-ended arrow. So P implies Q. that sort of thing. So if you ever see those arrows, that's what those mean. Now, how does this apply then to the last section? Well, if this is the conditional, the if-then statement over here, the converse would be if angles have special properties, all those angle pairs we learned, then lines are parallel. And after some investigation, this was kind of proven to be true, that if you can show that, say, corresponding angles are congruent, then the lines are parallel as a result. So we have every single theorem we learned last time now has a converse, and they are all true. The converse is true for each one. So what we would do is we would flip this statement for each one. So if the measure of angle 3 plus the measure of angle 6 was 180, then we would say L is parallel to M. So remember, last time we had to be given the parallel line, then we could say something. Now it's the opposite. If we're told that those angles are 180, they add to 180, then we know that the lines are parallel. And it's true for all of these other ones. So like if we only knew that 4 and 6 were congruent, we could say that the lines are parallel. Okay, and that's what these say. These will be a part of the word bank and up on the board for everyone. This is what I have on those reason magnets, is an abbreviated version. You know, writing this is quite a bit. Plus, this gets kind of straight to the point of like showing that the converse is implying parallel. It's saying, hey, you found the relative interior and that they were congruent, and that means that they're parallel. It could help when you're making a proof to know like where the implication is going, since now we have forward and backward stuff. Okay. So if 2 and 6 were marked as equal, that's a corresponding angle pair. And we know that if corresponding angles are congruent, then the lines are parallel. And then finally, if you had angles 1 and 7 congruent, then the lines would be parallel as well. Okay, so just remember that it actually ends up going both ways. Parallel lines means angle relationships, and angle relationships means parallel lines. That's really all I've told you today. Okay, and it just changes the style of questions that we answer just a little bit. For example, it's asking which lines are parallel. So we're searching. That's why the topic, the label for the notes is proving lines parallel. Okay, which lines are parallel if 1 and 2 are equal in measure? It would be A and B, because one, I would redraw the picture with just A and B, and the transversal that includes 1 and 2 near it. That's a corresponding angles are congruent implies parallel lines. Or we could refer to that as the converse of the corresponding angle theorem. So right here, well, I guess rather right here, we're saying that because we have corresponding angles that are congruent, we have parallel lines. And I know it's A and B because I've redrawn the picture, and the transversal crosses A and B. Okay, so let's try that again. If 3 and 8 are equal in measure, Which lines are parallel? Well, just circle your transversal, which, by the way, has to be touching both, angle slots in there, which means that L is parallel to M because, for one, those angles would be congruent because angles with the same measure are congruent. So you could say so by the converse of the alternate exterior angle theorem, L is parallel to. That's what this is saying here, alternate exterior, which is right here. If you have that matchup, then you have parallel lines. Okay, so my strategy or my advice would, again, draw a picture, and if you can put the angles so that they both are along that transversal. Remember, you only want one transversal in your picture. Okay, and then the two parallel lines, of course, will be the ones that are parallel because it's how the picture is arranged. If we had 1 and 4, what do you think? 1 and 4? Well, 1 and 4 are both on A, and A crosses we don't know they're parallel, but it crosses L and M, and because these are congruent, we use the converse of the alternate interior angle theorem, which means that L and M are parallel. Okay? But most simply, remember, if you have parallel lines, then corresponding angles are congruent. And if corresponding angles are congruent, then you have parallel lines. It's just simply going the other way. Okay? So we have these new names for things, but it's still literally just this. I mean, that could all be summarized by just writing what's highlighted right here. You could just write that. That would be perfect. You just have to draw a picture or somehow show me that it's LM and not AB. All right? And finally, now it mentions 3 and 5, but 3 and 5 are vertical angles. And vertical angles, there's no implication that lines are parallel. The answer to this is maybe. It's sometimes. Because we only have 4 ways to prove lines are parallel. Legitimately, we only have 4 ways. These 4 ways, and vertical angles is not one of the ways to prove lines parallel. Plus, if you know those 2 measurements, that means that these lines are free to go wherever they want, So it would be hard to prove that it's that one is parallel to the other. Because 3 and 5 are only in part of the picture. And you could move M freely because it's not connected to any of those angles. So that's another reason why there's just not enough. We don't know as many angles as we need to. All right. So this one says, find a value of X so that the lines are parallel. Well, okay. Well, if, angle 1 and angle 2 were equal, then L and M would be parallel because of the converse of the corresponding angle theorem. Right? If those were to match, they'd be corresponding angles that match, which implies parallel lines. So all you would need to do here is just ensure that these were the same, and the x value that does that is 30. Okay, so it's a big string of logic, but it goes something like this. If x is 30, then x plus 25 is 55. So angles 1 and angles 2 are congruent. And if those are congruent, then the lines are parallel because they're corresponding angles and they're congruent, which means that lines are parallel. Okay, so that's the string of logic there. So we'll apply that again here. If these two highlighted things were equal, what angle pair would we have? Do you know? It would alternate interior angles. Then alternate interior angles are congruent, which means the lines that are cut through by a transversal, this transversal, they're parallel. Okay. Makes me thinking too, like, if you have a picture like this, where like you have like all of the angles filled in like the same way, where it's like they alternate like that, that is the picture we're shooting for. It's basically saying if we have that picture, then we have parallel lines. These two being parallel. And that's kind of what we're saying here, is if those were to match, then that would be enough evidence to show that it's parallel, because that's just what the arrangement looks like when you have parallel lines. So to finish that equation, I think x is 50 there. So those aren't bad. It can get kind of lost in what you're trying to do, because I don't want you to just set them equal, because that's what you normally would do. We're setting them equal so that we can prove that it's parallel. Because if it's not equal, it's not going to be parallel. Again, we had a weird picture here, but we definitely know that this is the transversal because it includes both angles. So I'm imagining maybe extending these, because these look parallel, and for some reason the picture really confuses me here, so I would redraw it like this, and then you can definitely see that these are I would just need the word corresponding angles and then saying that they're congruent. That fact and this picture definitely show me that AC is parallel to RH. So these are parallel. Just because I know that this is something I'm comfortable with. So definitely maybe a hard one to navigate at first, but I just always try and identify the transversal, and the transversal is always the one, you can see it here too, is the one that includes like both angles. Both angles touch it. You know, L is not a transversal because it doesn't touch both of the angle pairs, or doesn't touch the angle pair. So same thing here. If the picture is making you lost, just imagine this as probably the transversal, and you could probably make a counter to me, but that's a good starting point. And then the other lines are probably going to be the parallel ones, but not until we redraw the picture, in my opinion, can you really see it. But if we make some extensions here, I start to see that, you know, that H shape, and we have both of our angles here and here, and they add to 180. So you'd want to write that somewhere and mention that same side interior angles are supplementary. which implies you have parallel lines. But the question is like, well, which ones? Well, it's got to be the ones that create that angle pair, right? So we would have KP is parallel to MN. Okay. So I would strongly suggest taking stuff from the picture rather than trying to just read the picture and understand its parts. Pull out the stuff that's useful. And that starts with finding the transversal. Okay, a couple proofs and then we'll be done. So this is the given. The proof to prove is going to be that A is parallel to B. And so that means actually something right away as well that you ought to write down. When you see this, you should be thinking it's going to be one of the ones that ends in that, or one of the ones that starts with the word converse. Okay, so we'll write both and you'll see it in just a second. So if these are the two angles that are given, I could state an important fact based on just this, that the sum of those angles together is 180. How do I know that? Well, you need to be careful. You only know that because it was given as a number, and we added those equations together. This is actually the addition POE. And I'll just do a quick verify. Yeah, that's what I was going for. Okay, so you are adding these two equations together. The left and the left were added, and the right were added. Adding equal things to both sides. That's addition POE. And that right there is talking about the fact that angle 2 and angle 5 are supplementary. Which is the definition of supplementary angles. And the reason I want that is because I know that if I go up to here, well, I guess you could kind of prove this in maybe more than one way. But the reason why I say that is because I know that the same side could be a little misleading, this one. The converse, or the same side interior angle theorem, or postulate, that is the answer. That is the answer of what goes in the box. But I also wrote that as, let's make sure I get exactly what I said so I don't. Same side interior angles are supplementary. Yeah. Same side interior angles are supplementary. Imply that you have parallel lines. This is a more like full reason, because it's saying that because you have supplementary, and notice here that the word supplementary is part of the implication or the given, the if of the if then statement. You got to have the word supplementary. So that's why I took this step. I could see someone going straight from here to here, and there's really like nothing that wrong about it, but we have to use what the theorem says. Okay, and the theorem uses the word supplementary. So anyhow, that's how you prove this. It's actually, there's not much to it. It's just the fact that, oh, these two add to 180, so that means that they're parallel, because if the same side interior angles there are add to 180, well, that's what happens when you have parallel lines, so that direction works as well. Okay? Maybe next time I'll sketch out the proof. So, like for this one, we're told that these are parallel, so definitely do lots of markings so you know. And then we're also told that 4 and 6 match. Okay? And we want to show that these are parallel. Okay? So if we look at the angles that we have labeled, and if we were to imagine maybe one of these becoming a new transversal to G and H, 5 and 6 are corresponding, like with parallel lines G and H. So recognizing that 5 and 6 are corresponding angles, if you just look at this picture, is huge. So like P is the transversal, right? If you have 6 and 5, those are corresponding. So that's what we could probably incorporate in our proof somewhere. So this is given. And then it actually starts off somewhere different, saying that 4 and 5 are congruent. And that's true because these are parallel. Meaning that 5 and 4 are congruent because we know that parallel lines imply alternate interior angles to be congruent. P and R being parallel tells us that. Okay? And then whenever you see this kind of game happening where you got two statements and 5 is 4 and 4 is 6, that's transitive. Okay, we've seen that at least 5 times up to this point, this kind of relationship. So this tells us that 5 and 6 are congruent. And that's what we're saying down here, is that they're corresponding as well. So not only are they congruent by this statement, but they're also corresponding from what comes from our picture right here. These are corresponding angles. So that's a perfect way to say that G is parallel to H, is that the fact that you have corresponding angles congruent, that implies that you have parallel lines. And that's the converse of the corresponding angle theorem. So whichever one you want to write is great. So you can pick between those two. But yeah, it's kind of an interesting, with having like two sets of parallel lines, it's tougher. But and let's just do a quick double check and make sure there weren't any surprises. Alternate interior, and then yeah, okay, great. So this is a good proof so you can see the difference between these two reasons. One of them is just the regular theorem itself. That's where we'll end, is just to look at this again. One of them, oh, and these section numbers are wrong too, darn. One of them is, if you're parallel, then you got your angle pair, and then we learn that you can go the other way. If this, then this. That's the big takeaway here from the notes. We'll practice more with the proofs